Chapter 10 is all about exponentials and logarithmic relations. In section 10.1, we are going to focus on exponential functions only. We will take a look at graphs of exponentials, as well as how to solve certain exponential equations, as well as inequalities. First off, there can be the equation for an exponential is f of x equals a times b to the x. Now, an exponential curve can be exponentially growing, or it can have an exponential decay. You've probably seen this in your science classes. Exponential growth occurs when b is greater than 1. An exponential decay occurs when b is between 0 and 1. So the a term out front does not affect the exponential growth or decay. Here are some other properties about an exponential function. We already said it's in the form y equals a times b to the x. A can't be 0, b has to be greater than 0, and b does not equal 1. The base is b, because that's the base of your exponent. Some characteristics of the graph is the function is always continuous, and it's also one-to-one. It passes the horizontal line test. Now, one-to-one also tells me that the inverse is also a function. That's what the definition of one-to-one means. The domain of an exponential curve is all real numbers. The x-axis is an asymptote of the graph, and we'll come back and talk about what this term asymptote means when we're together. The range depends whether my a is positive or negative. If my a is positive, then my range is all positive numbers. If my a is negative, then my range is all negative numbers. Now, the y-intercept is always 0, a. So that a value tells me my range as well as the y-intercept. Now, the graphs of y equals a b to the x and y equals a times 1 over b to the x are reflections across the x-axis, because y equals a times 1 over b to the x is the same thing as y equals a times b to the negative x. Okay, so whenever we see this negative in that exponent, that negative in the exponent tells me that it is a reflection over the y-axis. So in this example, determine whether each function represents an exponential growth or decay. Well, I just need to look at the b value. In a, since my b value is between 0 and 1, this is a decay. In b, since my b value is greater than 1, this is a growth. And in c, since my b value is greater than 1, it is also a growth. Oops. Now, since the domain of any exponential function includes irrational numbers, because again, the domain is all real numbers, so I can include the square root of 2 and all the properties of rational exponents. So in example 4, if I want to simplify these expressions, I simply just have to apply my exponent rules. When I'm multiplying with the same base, all I do is I simply add my exponents. So I have to remember my rules about radicals. I can only add radicals when I have the same number under the radical. So that's as simplified as that problem can get. In b, I'm going to multiply the square root of 2 times the square root of 3. So I end up with 7 times the square root of 6 The square root of 6 cannot be simplified, so that's my answer. Now, the property of equality for exponential functions. This is also known as the one-to-one property. And we will be using this property a lot to solve problems with exponential functions. And what it says is, as long as b is some positive number, which we'll have, if we have a problem where it's b to the x equals b to the y, as long as the bases are the same, all you have to do is set the exponent part to be equal to each other. And then you can solve that problem. For example, if 2 to the x equals 2 to the 8th, then x equals 8. So we're going to apply that here. In example 5, solve each equation. 3 to the n plus 1 equals 81. Well, 81 is not written as an exponent, but we know that we could rewrite it as 3 to the 4th. Now I would choose 3 to the 4th and not 9 squared because, again, I want the bases to be the same. Since the bases are both 3, then I can simply take what's in the exponent part and set it equal to each other. Now it's a very simple problem, and I get that n equals 3. Now in part B, it's a little bit more difficult, because I have 4 to the 2x equals 8 to the x minus 1. So in both of them, I'm going to have to change the bases. Because 4 can be rewritten as 2 squared to the 2x. And 8 is the same thing as 2 cubed to the x minus 1. Now I get 2 to the 4x equals 2 to the 3x minus 3. At this point, now the bases are the same, and I can simply say that 4x equals 3x minus 3, so x equals negative 3. Now the one-to-one property, again, we're going to refer to it as the one-to-one property, because that's how you're going to see it next year in pre-calculus. The one-to-one property also works when I have an inequality. B to the x is greater than b to the y. Same thing, you drop your exponent, or you drop your bases and keep the exponents where they are. And the sign stays the exact same way. Okay, so you don't have to flip the sign. So for example, if it's 5 to the x is less than 5 to the 4th, then x is less than 4. Now in example 6, I have to solve 4 to the 3p minus 1 is greater than 1 over 256. Well, hopefully we remember that 4 to the 4th is 256. But I need 1 over 256. So what that means is 1/4 to the 4th is the same thing as 1 over 256. But again, in order to apply the one-to-one property, I need the bases to both be the same. So the base on the left-hand side is a base of 4. So if I want to change this 1 over 4 to the 4th equals 1 over 56, what I can do is, remember, I can flip this fraction 1 over 4. I can flip this fraction 1 over 4, and by doing that, so if I flip it to 4 over 1, remember the exponent gets negated, and then what I do to one side, you must do to the other. Oh. That's the same thing as that. Okay? So what I could really say is 4 to the 3p minus 1 is really greater than 4 to the negative fourth, because 4 to the negative fourth is the same thing as 1 over 256. Now I can apply the one-to-one property and say that 3p minus 1 is greater than negative 4, 3p is greater than negative 3, so p is greater than negative 1. Here's our final example. This example is very similar to example 6. Hopefully we remember that 5 to the fourth is 625. So what that means is 1 over 5 to the fourth is 1 over 625. So again, if I flip the left-hand side, I get 5 over 1 to the negative fourth still equals 1 over 625. So applying that, I get 5 to the 3 minus 2k has to be greater than 5 to the negative fourth. Now I can apply the one-to-one property. 3 minus 2k is greater than negative 4. Negative 2k is greater than negative 7. And k is less than 7 halves, because remember, when you multiply or divide by a negative, you have to flip your sign of your radical.